This is the Kariba Dam on the Zambezi River, straddling the border between Zambia and Zimbabwe in Africa. Behind this massive concrete wall sits Lake Kariba, the world's largest reservoir by volume, holding 185 cubic kilometers of water. That's nearly 5 times the volume of China's famous Three Gorges Dam and more than twice the size of Russia's Bratsk Reservoir, the world's second largest. For nearly 70 years, this dam has stood strong, generating electricity for 2 entire countries and powering millions of homes and industries across southern Africa. But there's a problem. Beneath the surface, concrete is cracking, foundations are eroding, and the spillway gates are literally breaking apart from the inside due to a chemical reaction destroying the structure. Engineers warned that if this dam fails catastrophically, 3.5 million people living downstream would be in mortal danger, with economic losses exceeding $20 billion. That's why teams are now racing against time on a $294 million international rescue mission to save this aging giant. But they're facing not one crisis, but 2. This is the story of the world's largest reservoir and the desperate race to prevent a disaster that could reshape southern Africa. The clock is ticking. To understand why this dam is so critical today, we need to go back to the 1950s. Back then, this region wasn't Zambia and Zimbabwe, it was northern and southern Rhodesia, British colonies experiencing something remarkable: a mining boom. Copper, coal, chrome. They were being pulled from the ground at an unprecedented rate, and the mining industry needed one thing above all else to keep the boom going: electricity. Lots of it. There was just one problem. There wasn't nearly enough power to meet demand. So the colonial government made a bold decision: dam the Zambezi River at Kariba Gorge, the narrowest point along the entire river, with massive basalt rock walls on either side. The geology was perfect. An arch dam could curve into those canyon walls, using them to absorb the enormous pressure of the water behind it, rather than relying solely on the dam's own weight. It was an elegant solution. But here's the thing. They didn't just want a dam. They wanted the biggest reservoir the world had ever seen. Why go so massive? Because a giant reservoir meant guaranteed power for decades, even during droughts. With 185 cubic kilometers of water behind it, this dam could generate electricity year-round, no matter what. It was insurance, a long-term bet on industrial growth. And that bet was about to require one of the most challenging construction projects Africa had ever seen. Construction began in November 1955. The challenge? Build one of the world's largest dams in one of Africa's most remote locations and do it in just 4 years. The engineering team chose a double curvature concrete arch dam. At 128 meters high and 579 meters long, the structure would curve both horizontally and vertically, transferring the enormous pressure of 185 cubic kilometers of water into the canyon's solid basalt walls, rather than relying on sheer mass alone. This was the same design principle used on the Hoover Dam in the United States, which was being built at exactly the same time, just finishing in 1936. Both dams represented the cutting edge of 1950s dam engineering, using elegant curves and geology to handle massive water pressure. The scale of the Kariba project was staggering. Roads had to be carved through rugged terrain to reach both riverbanks. An airstrip was built from scratch, essential for emergency medical evacuations and rapid transport of critical supplies, since the nearest railway was 480 kilometers away. 2 entire construction towns were erected just to house the 7,000-person workforce. But the local Tonga people believed there was another problem engineers hadn't considered. According to legend, Nyami, a great river god believed to live in the rocks at the gorge, would never allow the dam to be built. In 1957, they were right, but not for the reasons they believed. The Zambezi unleashed what would later be called a 1,000-year flood, the highest flow ever recorded. Water poured over the top of the cofferdam, protecting the construction area. Bridges were swept away, equipment destroyed. 11 Italian workers were killed, their bodies later found in the wet cement of the dam wall. An additional 86 workers died overall during construction. The flood was so catastrophic that engineers had to redesign the spillway twice, increasing its capacity from 68 to 74 and finally to 92 cubic kilometers. And yet, despite this disaster, the project finished 6 months ahead of schedule. By the time the dam was completed in 1959, 86 workers had died on site. Over 1 million cubic meters of concrete had been poured. The cost? $135 million in 1950s money, roughly $1.4 billion in today's dollars. There was another cost, too. To create Lake Kariba, approximately 57,000 Tonga people had to be relocated from the Gwembe Valley, their villages and farmland disappearing beneath the rising water. Meanwhile, Operation Noah rescued about 6,000 wild animals between 1958 and 1963, a rescue that made international headlines while the human displacement went largely unnoticed. When Queen Elizabeth, the Queen Mother, officially opened the dam on May 17, 1960, the structure was complete. Lake Kariba stretched 280 kilometers with a surface area of 5,580 square kilometers, making it one of the largest artificial lakes ever created. It was a triumph of mid-century engineering, a concrete arc holding back an inland sea. And for the next 6 decades, it did exactly what it was designed to do. The Kariba Dam generates an impressive 2,130 megawatts of electricity capacity. The power is split between 2 underground powerhouses. The North Bank station supplies around 1,080 megawatts to Zambia's copper mines and industries. The South Bank station supplies roughly 1,050 megawatts to Zimbabwe's manufacturing and agricultural sectors. These two nations have managed this shared resource without major conflict for over 60 years. The Zambezi River Authority, established in the 1960s, coordinates operations between Zambia and Zimbabwe. It's one of Africa's rare success stories in transboundary water management. At full capacity, Kariba generates over 10,000 gigawatt-hours of electricity annually, clean, renewable power that drives the entire regional economy. But the dam's stability depends on 2 critical factors. First, the canyon walls and rock foundation must remain intact. Second, the spillway gates must function properly to release excess water during floods. Over the past 70 years, water cascading from the sluice gates at tremendous force has gradually eroded the bedrock at the base of the dam, carving out an 80-meter deep plunge pool. Here's where it gets dangerous. That erosion has been moving upstream toward the dam's foundation. If it reaches the base of the structure, failure would be catastrophic. And that's not even the worst part. The concrete in those 6 spillway gates has been expanding due to a chemical reaction called alkali-silica reaction, the same process destroying the dam's structural integrity. Over 60 years, this has warped the gates, making it harder for them to open and close properly. If those gates jam in the closed position during a monsoon flood, water could overtop the dam entirely. Combined with a weakened foundation, that scenario would be the dam's death sentence. These are exactly the problems engineers are racing to fix. Kariba Dam isn't just facing one problem, it's facing 2 massive crises simultaneously, and they're feeding off each other. Crisis 1: concrete breaking from the inside. In the 1990s, engineers discovered something alarming during inspections. The concrete in the spillway gates was literally cracking and warping due to alkali-silica reaction. This chemical process causes reactive minerals inside the concrete to expand over decades, creating internal stress. The problem? Those 6 spillway gates are the only mechanism for controlling water levels. If they fail to open during a monsoon flood, water can't escape. If they jam in the closed position, water backs up behind the dam and eventually overtops the wall. Either way, it's catastrophic. There's also the matter of foundation stability. That 80-meter erosion we mentioned? It's been creating weak points in the bedrock directly beneath the dam. If that erosion continues, it could undermine the dam's ability to transfer water pressure into the canyon walls, the entire principle that keeps an arched dam upright. The dam engineers were clear. These aren't problems you can patch. They're structural failures that demand urgent intervention. Crisis 2. The drought that makes everything worse. In 2024, Southern Africa was hit by a severe drought, one of the worst in 40 years. Lake Kariba's water levels plummeted to just 10% of usable capacity. Zimbabwe had to shut down its entire power station at Kariba South. Industries stalled, hospitals lost power. Millions went without electricity for days at a time. But the drought created a vicious cycle. The Kariba Dam Rehabilitation Project is partly funded by electricity revenue. When water levels drop, power generation drops. When power generation drops, the money to fix the dam disappears. So you have a dam with critical structural failures, but its own power output is too low to fund the repairs. Why not build a new dam? Here's the question everyone asks. Why not just build a replacement? The answer is scale. You can't drain 185 cubic kilometers of water without destroying 2 entire national economies. There's no alternative power source while construction happens. And unlike Switzerland's dam project, where they could build in front and drain the space between, Kariba has to stay operational the entire time it's being repaired. So instead, engineers are doing something unprecedented, saving an aging giant from the inside out while racing against time and drought. The window is closing. So, how do you save a dam that can't be stopped? In 2017, international partners launched the Kariba Dam Rehabilitation Project, a $294 million operation funded by the European Union, the World Bank, the African Development Bank, and Sweden. It was supposed to finish by February 2025. Instead, it's now scheduled to wrap up by December 31st, 2026. Why the delay? Because the problems turned out to be far more complex than initial inspections suggested. The work is happening in 2 main phases. Phase 1 tackled the plunge pool erosion. Engineers built a massive cofferdam to isolate the area, then excavated and reinforced the damaged bedrock with 5,241 cubic meters of concrete. This component was completed in July 2024, with the cofferdam removed by October. It was a critical milestone, stabilizing the dam's foundation before further damage could occur. Phase 2 is the spillway refurbishment. This is the real engineering challenge. 6 sluice gates, each deteriorated by decades of corrosive water and concrete degradation, need to be replaced with chemically resistant alternatives. As of October 2024, the work is 82% complete on 4 gates. The remaining 2 are on the critical path. One delay cascades the entire timeline. All this work is happening on a functioning, power-generating dam. Engineers can only operate during the dry season when water levels are low enough to access the structures. They cannot shut it down. Low water means less power generation. Less power generation means lower revenue. Lower revenue means less money to fund the repairs. It's a race against physics, drought, and the calendar. Yet somehow, Zambia and Zimbabwe have managed to keep this project moving forward together, coordinating through the Zambezi River Authority, sharing the costs, agreeing on priorities. It's not perfect, but it's working. And it has to. In less than 2 years, the dam's future will either be secured or it won't be a dam. If we zoom out, Kariba isn't just about one dam. It's a preview of what's coming across Africa. Over 200 large dams dot the continent, most built during the colonial era or between the 1950s and 1980s. Today, they're all aging at the same time, facing droughts and extreme weather their designers never imagined. The Kariba rehabilitation is a test case. If it succeeds, it shows how African nations can manage their aging mega-infrastructure. If it fails, the consequences ripple across the region. But it's also a warning. The $294 million bill for Kariba reflects decades of deferred maintenance, colonial-era infrastructure handed to newly independent nations without resources to maintain it. Across Africa and the developing world, hundreds of dams and power systems built in the mid-20th century are reaching the end of their design lives. Kariba isn't just one dam's fight for survival. It's a race against time for an entire generation of aging infrastructure. What do you think? Drop a comment and subscribe to Megabuilds for more stories of engineering at the edge of what's possible.